In this video, we're going to try to develop a bunch of limit laws. Different rules that are going to make it easier for us to compute more complicated limits by breaking them down into easier limits. So for example, suppose that what you had was the sum of two different functions, like e to the x plus x cubed. And then you wanted to figure out what the limit was as x went to some particular value. Can you do something about that? Can you use the fact that this is a sum to help you in some way? So I'm going to give you an example of a few different functions. So what I have here is a function f of x that goes up here and goes flat. I've got a g of x, goes along, goes down. And then what I've sketched up here is the function f of x plus g of x. It's a new function, but it's a function that's built out of these other two ones. And you'll notice, for example, that if I take the value of f at 0, which is 0 plus 2, 0 plus 2 is 2, so the start of f of x. Or here, it looks like this is height of 1, and then we've got a height of 2, and then we've got a height of 3, which is 1 plus 2. So indeed, everything seems to work out relatively nicely. That is indeed the graph of f of x plus g of x. Now, I'm going to focus, just for fun, at what the limit was if I chose the a equal to a half. So I'm going to go and look up here all of the halves. So if I was just to do f of x, then I could come around here and I've got this 1 point there, and the limit of f of x at the value of a half is just going to be equal to this 0.5. So I'm going to say the limit as x goes to 0.5 of f of x, this is equal to, looks like, a 0.5. All right, lovely. Okay, so now let me do the same story, but I want to look at it for the g of x here. So a g of x, it looks like it's got this height up here of 2. So I'm going to say that the limit as my x goes to 0.5, but not of my f now of my g of x, that this is going to be equal to 2. That is that the limit as x goes to 0.5 of now my f of x plus my g of x, the sum of those two functions, that what it appears to be is equal to the 2.5. Now what I want you to observe is that a half plus 2 is equal to 2.5. In other words, it looks like that the limit of a sum is just the sum of the two limits. So indeed, this is the formula that we have. The limit of the sum of two things is the sum of two different limits added up. That I can sort of take this single limit and distribute it over this particular summation sign. Or at least that's what it appears to be. Is this formula always true? Well, let me show you a specific example. All right, let's do the limit as x goes to the value of, I'm going to do the sum of two functions. It's going to be the function 1 over x and the function minus 1 divided out by x. Which 1 over x plus minus 1 over x is just a different way of saying that this is just going to be equal to 0. Because indeed they cancel. So then the question is this the case that I can say that this is equal to these two individual things? The limit as x goes to 0 of 1 over x plus the limit as x goes to 0 of minus 1 over x. Is it the case that this is true, that this thing on the right-hand side is equal to 0? However, the problem is that neither of these two limits actually exist. Indeed, the graph of 1 over x is something that looks a little bit like this. And then the minus sign is going to flip it for the other. This is something where the limit has this vertical asymptote at this particular point of x equal to 0. So this does not exist, and this other limit does not exist. So this whole formula is actually kind of nonsense in this scenario because this doesn't exist, doesn't equal any number. This doesn't exist, it doesn't equal any number. Yet we're saying that they add up together to be equal to this 0. So what's the problem with my example? Because I like my formula, we were well motivated by it in the previous example, but for this example it appears to be nonsense. And what is needed is an extra qualification. This is true if we have the property that both the limit of f of x and the limit of g of x individually exist And that was the problem here. These individual ones did not exist, and so you sort of got this nonsense formula. But if you add this property, then we get this true statement. So this is one of these so-called limit laws, a law that allows us to break up a more complicated limit into a simpler one, but there are many. So for example, if you have some constant, some just real number like 7, the limit of 7 times f of x is just 7 times whatever the limit was of f of x. Or we had this so-called additivity rule here, but we can do the same thing with products. We could say that the limit of a product is the product of 2 different limits here, again under this initial assumption that all these individual limits exist. The same thing with quotients. We've got to check for non-zero here, but if I have an f of x over a g of x, this is the limit of a quotient. It is the quotient of a limit, provided we have this additional assumption that the one on the bottom, the limit of the g of x, is non-zero. So these add up to be a bunch, not all, but a bunch of the different limit laws that allow us to break up more complicated limits.